I am very excited to introduce Natasha Latouf, who is a graduate student at George Mason University, finishing up this year. Next year, so very soon. And Natasha, I will turn it over to you. Thank you for speaking to us.
Thank you, everyone. So today I'll be presenting actually kind of an abridged thesis talk. I recently advanced to candidacy, so I'll be covering both sides of my thesis. So I'll be presenting both BARBIE, the Bayesian analysis for remote biosignature identification on exoEarths project, and then I'll also be presenting my work on effective and ethical encryption. So ever since the first exoplanet was discovered now, almost 30 years, over 30 years ago, we've discovered and confirmed over 5,000 planets since then. And so now we want to go into the next age of exoplanet science, which is characterization over detection. And looking at terrestrial exoplanet atmospheres is one of the best ways that we can understand our own Earth's development, as well as understanding what else is out there and how rare we are in this universe. And so with the proposed future missions, such as Habitable Worlds, Life, we can probe for biosignatures that can hint at planet conditions, and by looking at these biosignatures, we can understand the abundances of potential biosignatures and what different methods of biology might look like through the universe. So to introduce coronography very briefly, I'm sure most of the people in this room don't really need it, but I'm gonna go for it anyway. Coronography allows us to directly image a planet's light, and so by using this method, that we can probe more deeply into the planet's atmosphere that we are interested in looking at. And since the inner working angle of coronagraphs is proportional to wavelength, it favors then shorter wavelengths. However, there are some biosignatures, many biosignatures, that have prominent features at longer wavelengths. So understanding this give and take of what the instrument requires versus what biosignatures are more easily probable at what wavelengths is crucial. So we need to do this in order for us to have efficient observing procedures so that we can inform the telescope design as it's being put together now, and then also be ready to observe when it's on sky. So here we have the very famous GIF that's been seen about 100 times of a coronagraph blocking out the star that 3 planets are orbiting around. So we begin with BARBIE 1. Detecting water usually stands as the first step in the search for habitability, just because it's such a prominent feature. And there are multiple factors that affect the efficacy of atmospheric characterization, including at varying wavelengths, including most prominently signal to noise ratio, SNR. And if we vary the molecular abundance, we can study multiple Earth epochs and understand how the abundance of a molecule changes the detectability of that molecule through wavelength. So studying H2O specifically, here on the left, I have varying H2O abundances, 3 times 10 to the negative second, volume mixing ratio, 3 times 10 to the negative third, and 3 times 10 to the negative fourth. Where here in our simulations, 3 times 10 to the negative third is modern Earth, and that's the center pink line. And so you can see that moving up or down by a factor of 10 drastically changes the detectability, especially when you look at this feature hovering around 0.9. So we want to really investigate what SNRs are required for us to detect water, especially at this usually first probed feature at longer wavelengths. So for our methodology, we use the pre-computed spectral grid from Sisomil et al. That's actually published, not submitted. Apologies. And then we give it a fiducial spectrum that's split into 25 band passes of 20% width from 0.5-ish to 1 micron. So really, we're only probing the optical range in BARBIE 1. For all of our abundance case studies, we leave all of our values to modern Earth values, except for water, which we vary across abundance space. Now, this isn't technically chemically accurate, but it's a good first step to understanding how that feature by itself changes the detectability necessary. So we submit these to the nested sampling routine PSG nest that's built on multi-nest, and we do that using Grid Runner, which enables us to submit thousands of configurations very quickly. So where retrievals can sometimes take on the order of days or weeks, we can run thousands of retrievals in a matter of hours, actually. It actually is about 34,000 retrievals, took about 6 hours. So very, very quickly. And from this, we get our outputs, which are the highest likelihood values, posterior distribution, uncertainties, and most importantly, the log evidence. So the log evidence is what we use to calculate the log base factor, natural log of beta, as described by Beneke and Seeger et al. We use this to determine detectability instead of a sigma detection metric, because by definition, a 68% credible region will contain the true answer 68% of the time. Whereas the log base factor actually investigates the likelihood of fit of the spectrum and finds the best fit of a spectrum that has the molecule in it versus one that does not have the molecule in it. So it's really probing whether the spectrum is better for having the molecule there or not. So this is a better measure of detectability, which I'll get into shortly. No, you're good. Go ahead. By all means.
Sorry.
Go ahead. Don't need it. So here on the left, I showed the spectrum. Up at the top here is a resolving power of 500. This is the native resolving power of the grid, so it's very high resolution. Then I have a resolving power of 140. This is what we use, so we bin down the R of 500 to 140 to get to a more realistic looking spectrum. And then I also present a resolving power of 70, just so that we can show how much more broad the features get and how much granularity you lose by binning down resolving power. I also show here in the purple dots, the bandpass centers for each of the 25 bandpasses. And then the first and last 20% bandpass is shown in the gray. So you can see by having 25 of these, we are very, very finely observing the spectrum. And this was done purposefully so that we can have a very, very granular perception of what the detectability does. So, there it is. Okay, so I present first the results for the modern Earth simulation. So we have not buried the abundances here. So here is where all of my explanation of the Bayes factor coming into play. So here we show what an unconstrained detection, so natural log of beta of less than 2.5. So we are not constraining this molecule at all. We are not detecting it. Then we have a weak detection shown in the pink diamonds. So that's a natural log of beta between 2.5 and 5. And then anything 5 or over is a strong detection shown in the purple squares. And we show this as a function of wavelength abundance for each SNR. So we go up in steps of 2, and we can see that at an SNR of 6, we're strongly detecting water at this 0.9 feature for 4 band passes. And this remains the case for an SNR of 8 all the way up to an SNR of 10, but we're still not detecting water at shorter wavelengths, which is what we'd be interested in looking at for multi-species constraints and also to adapt to the coronagraph's capabilities. We're still only getting weak detections here. But then by the time we go to an SNR of 12, we're suddenly strongly detecting at around 0.74, 0.75, 0.8. And so we really wanted to take a look at that feature and that detectability range. So we zoomed in a little bit and tried to look at it more finely. So we looked at an SNR of 11, 11.5, and 12, so that we can really study what's happening here. And we can see that at an SNR of 11, it's essentially the same result as an SNR of 10. The 68% credible region is a little bit more constrained to the true value that's shown in the dotted line, but not much more of a difference. At an SNR of 11.5, we see these two band passes suddenly become strongly detectable at about 0.76 and 0.77-ish. And then by an SNR of 12, we're really picking up the entire feature. So really, it didn't take very much of a change in SNR for us to suddenly be strongly detecting this feature. So really narrowing down the SNR requirements becomes much more crucial when you see how fast the detectability can change, just in a matter of 0.5 of a difference in SNR. So then I present here the abundance case study. So we varied the abundance based on the literature, going from 3 × 10⁻⁴ volume mixing ratio, so about 300 parts per million, all the way up to 3 × 10⁻² volume mixing ratio, about 30,000 parts per million. And you can see here that at the 0.9 feature, which is what's being shown, your left, my right, even at the lowest abundance in our simulations, you can strongly detect it once you get to an SNR of 12. And then once you get to 1 × 10⁻³ volume mixing ratio, which is not that much more, you're already dropping in required SNR to an SNR of 7, because here we're showing, the heat is the log phase factor, so we're looking for this dark purple as we want to see. When you look at the 0.74 micron feature, the shorter wavelength, it's a different story. You cannot strongly detect at the lowest abundance that we assumed in our simulations. In fact, you can't really strongly detect it until 1.7 times 10 to the negative third, so about 1,700 parts per million. Which again, comparing to 3,000 parts per million for a modern Earth, there's not very big of a difference there. And even then, it would take an SNR of 16 to strongly detect. So really, a modern Earth is the first time that you're able to get a strong detection at mid to high SNR data at this lower feature. So this is a really crucial result that prompted us to look a little bit further. But we wanted to put this in context of Earth through time, right? That was our original exploration here. So we present here the 4 features of interest for water. So here we have 0.9, 0.85 micron, 0.83, and 0.74 micron. We show these as a function of abundance and SNR. And then we also show from Rocky 3D simulations, the presumed ranges of abundances for different epochs of Earth for water. So we can see that water is only detectable at 0.9 and 0.85 microns for the low abundances of less than 1.7 times 10 to the negative third, as we saw before.
Sorry, I lost one bit. This curve, these curves here are the threshold between what, like non-detected and detected?
These are only strong detections.
Strong detect, from there upwards is all strong detected.
Yes.
Okay.
So these are only strong detections that are shown here.
Alright,
Thank you for catching me there.
Mhm.
So even then, we can only detect the, at low abundances at high SNR, even at 0.9 micron, which is the most deeply absorbing feature, you need an SNR of 12 to detect. When you get to water abundances above 1.7 times 10 to the negative third, so again, you're getting closer to a modern Earth, that's when it's detectable at all wavelengths of interest. But again, it depends which SNR you're looking at, because for the shorter wavelengths, you require high SNR, while for the longer wavelengths, you don't require a very high SNR, about mid-level. When you take a look at how this fits into varying Earth epochs here, right? You can see that a Neoproterozoic is very unlikely to be detected due to its lower abundance values, where a mid-Cretaceous greenhouse or a modern Earth are more likely to be detected at a variety of abundances. Now, water doesn't have very many geochemical proxies on Earth to let us know the abundances through time with very much accuracy. So all of these points you have to take with a grain of salt, right? Because we're trying to estimate how much water could have existed at multiple times during Earth's history, and that's not very well constrained. However, when you look to O2 and O3, they have geochemical proxies that allow for much better estimations of Earth through time, which brings us to BARBIE 2. And we'd really be interested in studying the oxygenation of Earth's surface, which usually stands as the next step after water to look at for detectability of biosignatures. And we can help understand on our own Earth the global biochemical development. So here we show again another version of the abundance plot, except here we're looking at varying O2 and O3 abundances, again at a resolving power of 140, which is what we use in our simulations. We show in the light pink 3 times 10 to the negative 6, so an early O3 volume mixing ratio. We also show in the light blue, just so we can see, about a 50% of the present atmospheric levels of O2 volume mixing ratio. And then we show again the modern Earth in the dark purple to see the differences. So you can see that O3 absorbs very quickly, where a modern Earth level of O3 is 7 times 10 to the negative 7 volume mixing ratio. By 3 times 10 to the negative 6, it's this huge absorbing feature. So it doesn't take very much for O2 to really saturate. Versus for O2, you can see that even at a modern Earth level, and then going to 50%, I'm not sure how well you can see, but really the deepest absorption peak is here compared to here at modern Earth levels. So O2 changes quite rapidly. So again, we present the same results for modern Earth, 20% bandpass. On the left here that I'm showing is O2, and you can see that at an SNR 6, you're getting a weak detection for any bandpass that contains any portion of the O2 feature. By an SNR of 8, you are strongly detecting O2, and at all above SNRs, you are strongly detecting O2. And essentially the only thing that changes is that the 68% credible region narrows and narrows as it becomes a much firmer detection. For O3, this is a much different story. You'll notice here that I have to start at an SNR of 16 in order to get even a weak detection at any point in this wavelength range. And it takes until an SNR of 19 before you're getting strong detections at any band passes. And we only get strong detections for 2 band passes. Even by an SNR of 20, you're only getting strong detection for 3 band passes of O3. This is because, largely due to the reason that O2 is a very sharp, narrow feature. Once you've detected it, and it's very deep. So once you got it, you got it. Versus O3, especially in this region, O3 is much more active in the UV. So for O3 to be detected in this region, it needs to really be deep. So then we take a look here at the minimum bandpass, the shortest wavelength bandpass at which you're getting a strong detection, or in this case, a weak detection of O3, because we want to compare where all of these molecules are detectable as a function of SNR, as a function of wavelength, and where they are detectable together. So we can see, as we saw before, that O2 is this nice little rectangle of detectability. You can start to strongly detect O2 starting at an SNR of 8, going all the way up to an SNR of 20, and the shaded region shows you the width of band passes that you're able to detect. So you can start with the lowest band pass around 0.69 center, all the way up to about 0.8. Versus O3 is strongly detectable at 0.63 in this little region here, but it's weakly detectable starting at 0.6 at an SNR of 14. So what does this mean when we look at multi-species constraints? So we present here as well in the pink squares, a strong H2O detection as a function of wavelength so that we can observe how each of these things change together, as I mentioned. We can see that at an SNR of 10, at 0.83, we can strongly detect water and O2 together, because this is the longest wavelength at which O2 is detectable, while at the same time being the shortest wavelength at this wavelength that H2O is detectable at. So this is very promising. An SNR of 10 is accessible to us. At an SNR of 17, you can strongly detect water while weakly detecting O3, but there is no point at which you can strongly detect O3 concurrently with any other molecule at this point. So when we put this in context for Earth's history, we again show the same plot that we looked at before. The difference here is that the shaded region here to the left is modern O3, and this is early O3. And for O2, we can show where the modern level of O2 is, but based on what the literature says a Proterozoic Earth would have 0.1 or 1% O2, it's actually very far off of the chart here. So O2 is not detectable lower than 50% of the present atmospheric level of O2. So it's highly unlikely that a Proterozoic abundance level of O2 could be detected, considering we're looking at 0.1 or 1% of O2 for those. O3 is detectable across the entire range of abundances that we looked at, so that's promising. But it's most detectable at at early Earth levels of O3, both weakly and strongly at low SNRs. So O3 presents much more promising to detect across Earth time, where O2 is easier to detect now. But all of this has been done for a 20% bandpass. So we want to take a look at what varying the bandpass width would allow us to study, and if that introduces any change to detectability strengths. For the current coronagraph design for HWO, it's not necessarily set yet whether what the bandpass width is going to be, and there's still discussion of, for instance, sending up more than one coronagraph, so we can be combining this. So it's really crucial that we understand if any molecules change in detectability based on the coronagraph. So here we show the varying O3 abundances. Again, so there's a modern volume mixing ratio, or a modern Earth, an early Earth, and then a midpoint Earth here shown. And then I show in gray, again, a 20% bandpass, and in light blue, a 40% bandpass. So you can see how much more of the spectrum we're picking up by increasing the bandpass width, which allows us to establish a better continuum, and ideally that would help change the O3 detectability. And we do in fact find just that O2 detectability does not change significantly across bandpass width. Again, since O2 is such a narrow feature, once you've picked it up in your bandpass, you've picked it up. So increasing the bandpass width and having more continuum, while helpful for other reasons, doesn't change your O2 detectability. Whereas for O3, it changes significantly across bandpass width. because the ability to pick up more of this very broad feature really increases your ability to detect it. And you can see here, so from 20 to 30 to 40% bandpass, even by 30%, you can dual or triple detect strong O3, strong H2O, and strong O2. And by 40%, basically all of these regions are completely overlapping for dual or triple detection. So by varying the bandpass width, we can access a greater range of simultaneous molecular detection, which would be great for our efficiency in observation strategies. Of course, I mentioned before that we aren't being thermochemically consistent because we are only varying the molecule of interest when we are looking at varying abundance studies, but of course this is not correct. So we tried to change this a little bit by doing an O2, O3 coupled abundance. Again, this is still not as chemically accurate as you'd love to see, but for efficiency purposes, it still gives us a good first metric. So we use the Kazakis et al. Paper to pick our values because they have the coupled O2, O3 values as a function of multiple different stellar types. So we were looking at a sun-like star and we took a look across the range of their curve there. And so our abundance pairings were 100% present atmospheric levels of both, which is what we'd already looked at for modern Earth. We did 50% O2 and 110% O3 of the present atmospheric levels. And then we looked at 10% O2 and 105% O3 for the present atmospheric levels. Again, you really don't need to vary O3 all that much to get a pretty big shift in detectability. So we present here the 50% O2 and the 110% O3 versions. There is a chart of 9 of these in BARBIE 2. I highly recommend that you go look at them because I had to make each one by hand and it was a pain. So we can see here that we show the regions of dual, triple, or single detectability. So the hatched regions are single detectability regions and the molecule that you're detecting is labeled. The shaded regions are any dual detection regions, and the shaded regions that are outlined in black are any triple detection regions. And again, all of the molecules that you're looking at there are labeled. So we can see that H2O is the one limiting dual or triple detection with O2, for instance, in both SNR and wavelength, because O2 is just like, have seen, right, this nice little rectangle, and H2O actually varies as a function of SNR and wavelength, what SNR is required for each wavelength. And we can see that H2O is again limiting in SNR for O3, but O3 is the limiter for dual detection in wavelength because the O3 feature only goes out so far in wavelength space where H2O continues out to 1 micron. So we can see here, most interestingly, that triple molecular detection is possible at 30% and 40% bandpass widths. Once you get to a 40% bandpass width, actually, you're almost never detecting a molecule by itself. You're dual or triple detecting across your entire wavelength space for the optical, whereas at a 30%, you can still detect by itself O2, O3, and H2O, depending on what your SNR wavelength requirements are. So this is huge. So based on what wavelength you're interested in, what SNR you're capable of achieving, we can find out exactly what it is that you'll be able to detect. I made that sound a lot stronger than it is. All of this is, of course, simulation, so who knows what might actually happen. So we look then to BARBIE 3. So this is the varying H2O abundance plot that we've known and loved, I've shown you before. And it's very fruitful, it's very useful. But here we're only looking at the optical, and when you look at looking at the have worlds possibilities of wavelength space from 0.2 to 2 micron, for instance, we're really covering a very narrow region here. So even though it's a very fruitful region, it's still narrow. And we don't really know what's going on outside of that region as far as detectability goes, even though we know that many molecules absorb outside of this region or simply exist outside of this region at all. And there are, as I mentioned, lots of other features and phenomena that we can study by expanding our wavelength range. Thus, in BARBIE 3, we introduce the CHEM. It is a new set of 4 geometric albedo spectrum that range from the UV to the near infrared from 0.2 to 2 microns, as I mentioned. We've increased the amount of molecular parameters. So now we have methane, carbon dioxide, CO, SO2, and N2O, along with the previously included H2O, O2, and O3. And orthogonal parameters are not included in one grid. So any parameters that do not overlap in molecular space are not available in one grid because there isn't the possibility of false positives or false detections since they don't overlap. So here I show the four grids that we've developed and the spectrum, what the spectrum would look like for a modern Earth. So the top grid, all these names are subject to change, so don't get too attached. The Natasha grid has H2O, O2, and O3, so it is the replication of the SysML grid that we've been using, just expanded out from 0 to 2 micron. Next is our methane grid. It has H2O, methane, and carbon dioxide, so you can see that we're missing the O2 features and O3 features here, while picking up all of those nice methane and CO2 features. Next, we have our carbon grid, which is H2O, CO2, and CO. So again, we're missing a lot here in the UV, but that's okay. And then we have our oxygen grid, which is O3, SO2, and N2O, which basically only has activity in the UV and nothing else for the entire rest of the wavelength range, which is okay. So each of these grids can be used to study either the molecules of interest or to probe a wavelength range of interest, since each of these is active in different places, such as using the oxygen grid to probe the UV. And because each of these have the same 3 bulk parameters and then combined with different molecular parameters, we can actually also do multiple retrievals across grids and combine the results together to make one Frankenspectrum, in theory. So by using the KEN, we can explore new planetary types and varieties. So looking at atmospheres that are CO2 or CH4 rich rather than O2 rich, which is what we've been doing, looking at different planetary types like a Venus or Mars-like planet. And so by using the KEN grids, we can explore these new wavelength and parameter ranges and quantify the observation trade-offs as a function of bandpass width, SNR, and wavelength, which is of course so very cool. So I'm going to present my conclusions for BARBIE here. So H2O, O2, and O3 can be detected simultaneously as low as 0.66 microns, which is great for coronagraphs, at 30% bandpass with a moderately high 13 over SNR data. The new grids that we've developed unlock new possibilities for detection and simulation across wavelength and parameter spaces. And then by understanding the SNR and bandpass width requirements for detecting molecules of interest and then properly prioritizing the spectral bandpasses to observe, then we can have the best instrument designs and observing procedures to be ready to go when we're on sky. So at this point, I'm going to shift tracks a little bit to the other half of my thesis, which is the study of effective and ethical mentorship in physics and astronomy. So the Habitable Worlds Observatory is going to be a multi-decade effort spanning generations of scientists. And there are historical and systemic barriers that have resulted in extremely low rates of recruitment and retention for historically minoritized groups, HMGs, in physics and astronomy. And even though mentorship was designated as a priority moving forward in the 2020 astrodecadal, with an emphasis on research-based techniques, no work has actually been done to realize that plan. So we have a chance here with the Habitable Worlds Observatory to introduce for the first time a mentorship program at the ground floor of the observatory, which is being considered right now. But if we do it right, we could use this as a mini experiment to see how ethical mentorship practices could change the face of the field. So to motivate a little bit, students from historically minoritized racial groups earned only 16% of bachelor's degrees and about 6% of PhDs in astronomy in 2014. This includes Black, Latina, and Indigenous people. This does not include many other racial groups that are still designated by the US government as historically more minoritized, such as Arabs and Arab Americans. Women earned 21% and 33% of the bachelor's degrees in physics and astronomy, respectively, since 2017. However, since 2017, the amount of physics and astronomy degrees awarded has gone up, even though these numbers have stagnated. So even though more physicists and more astronomers are graduating out, the same percentage is still women or historically minoritized racial groups. And when you take a look at intersectional identities, so taking a look at gender and race, for instance, the numbers plummet. So of the 59,894 PhDs in physics that were awarded between 2017, 1972, and 2017, so almost a 50-year period, 90 were awarded to Black women, which is 0.15% of all the physics degrees in about the last 50 years. So, horrifying. We can reduce barriers through mentorship, however, for these historically minoritized racial and gender groups. So there are multiple different kinds of barriers. I will be going through each one. So imposter phenomenon can be mitigated through careful mentor-mentee pairing. Stereotype threat, which has been shown to negatively impact historically minoritized groups, can be combated with culturally responsive mentorship. Mentorship relationships improve a sense of belonging and social connection in a field, which is crucial for minimizing othering. And microaggressions can be addressed through mentoring with dialogues and positive micromessaging. I'll go through each of these. Oh. I don't have an explanation for what just happened, so we're just gonna go with it. So, starting with imposter phenomenon. This is defined as the feeling that one is not as intelligent or capable as others perceive them to be. So you feel like you're faking or like you're lying to everybody. And this is historically known as imposter syndrome. That might be what you've heard before, but that indicates that the fault lies with the person, that you have a syndrome, when actually it's the fault of the oppressive system that you feel that way. So we're moving towards imposter phenomenon. So students from historically minoritized racial groups can experience higher rates of imposter phenomena due to a lack of diverse mentors and role models that are available to them. If you can't see someone that looks like you or can aid you in understanding your life experiences at role model levels, at higher levels in your career, then it becomes a self-fulfilling prophecy that you believe you don't belong there because you don't see anyone belonging there. And this can result in many mental health concerns, leading to spirals, which can then result in heightened mental health concerns. So, for instance, you feel like you don't belong and that you're lying to everybody, so you don't study for an exam because you feel like you're gonna fail anyway because you don't belong there. You don't study, so you fail the exam, which proves to you that you were right, that you don't belong there, and this just spiral continues and continues and continues until you either drop out, burn out, or leave the field. So then you also are facing stereotype threat. So this is defined as the negative impact of identity stereotypes when you are engaging in activities that are related to those stereotypes, all right? So this can result in science disidentification. So you find yourself belonging to groups that you don't actually want to be belonging to, and that leads to a decline in physics identity and career persistence. So a good way to think about this is if you ask someone to use 5 words to describe themselves, there would be a higher rate of people from historically minoritized groups that would not use the word scientist, physicist, astronomer, insert here, to describe themselves in the 5. Whereas other people might have a much stronger sense, I am a scientist, I am a physicist, and use that to describe themselves. Stereotype threat is also prevalent at the faculty level with the same effects that are noted at the student level. So then less historically minoritized groups are found at faculty levels, and those that are at faculty levels are reluctant to pursue other leadership for fear of being impacted by this stereotype threat continuously. Then we also have othering. So this is defined as low levels of social connection and belongingness due to exclusion from other groups. And that can lead to a reduction of your interest in STEM and very low retention. So this is why peer mentoring is an incredibly important part of mentorship practices. Students from historically minoritized groups experience othering at a much higher rate, especially when they're going to predominantly white institutions, PWIs, and that can lead to social separation from their peers. Whether that is because they separate themselves out because they do not feel that they belong, or the group themselves separates them because they are saying you don't belong. And then feeling isolated from their community is an essential component of low retention for historically minoritized groups, which leads to the impeding of their success. They are more likely to leave to try to find community than they are to stay in a field where they feel they don't belong, and in fact, continuously teaches them that they don't belong there. Then we come to microaggressions. So these are defined as covert, occasionally unconscious. The word occasionally is doing a lot of work here, it's usually quite conscious. Subtly disruptive phenomenon used to bring down other groups. So there are actually three distinctive types of microaggressions. It's all under the same umbrella, but they vary slightly. So you have micro insults, which are conveying rudeness through behaviors, through actions or verbal remarks, right? These are the things where people say, oh, I just wasn't thinking when I said it. It's those. Micro invalidations, so then you're using actions to exclude, negate, or nullify the lived experiences of historically minoritized groups. So say someone comes to you and says, hey, I just had this really weird experience with this person, and somebody goes, oh, no, that person's great, don't worry about it, they're a good person, you don't have to worry about that, and just completely nullify your own lived experience. And then micro assaults, they're not very micro at all, that's like outright racism, so that's just explicit put downs at that level. And these can create a hostile environment towards historically minoritized groups, which leads to a much higher probability of burnout or field departure. Again, you have all of these cases working against you. And unfortunately, what I think is the most important here are false allies. So you end up with a lot of people that call themselves allies, that say that they care, and they position themselves as a champion for the people, while actually they are maintaining the culture of ignorance by not actually doing anything. So you see multiple themes with these people. So you see physical distancing. They're saying, I'm an ally, but nothing happens in my classroom, in my field, in my research group, in my lab, et cetera, et cetera. Therefore, I don't have to do anything because it's not happening here. Or you see that the problem is too big for them to impact. So they say, well, it's the fault of the K through 12 system. There's historical legacies of sexism and racism, socioeconomic factors. It's not my fault. It's too big. I can't change it. Or you see, I am helpless to act, therefore inaction is justified. So they recognize that the problem is very big, and they think, oh my gosh, I can't do anything about it. Therefore, they justify to themselves that they don't have to do anything. Somebody else will do it, but they'll still call themselves an ally. On a side note, this Darcy and Hadari paper is phenomenal. I highly recommend reading it. So you can reduce barriers through mentorship. Deja vu, I went through this, my apologies, everybody. Mentorship can help alleviate all of these things, and I will go into it a little bit further here. So additionally, you can help students find a sustainable balance between their scientific research and their commitment to the field through effective and ethical mentorship. You can provide a sense of community and ownership, and you can increase satisfaction with their career in the long term. Now, these are known effects to mentorship, but the important part here is the effective and ethical mentorship. A lot of people call themselves a mentor without actually knowing how to mentor properly. So a big broad recommendation is creating what is called a holistic, non-dyadic mentorship model. It's constellation mentorship. I will get into that. You should establish an overseeing team or committee for this mentorship team. And you should implement practices to minimize the emotional labor burden. Traditionally, a lot of the people that are doing the labor of improving access, improving justice, improving mentorship are people from historically minoritized groups. And so putting in practices that minimize the emotional labor and who's actually volunteering to do these can be a great way to mitigate that. And you should also provide mentorship training, required mentorship, if you ask me. So this is a good figure that presents what a holistic non-dyadic mentorship model could look like, right? So you have a grad student in the middle. They are connected to their peers, which can help alleviate othering. They should be mentoring an undergrad of some kind, somebody in a younger career stage, and then they have a faculty member that they go to. So this is one good example, but I feel that it's missing just a few small things. Another good example is from the Byers-Winston 2019 handbook. So when you look at specifically the network is what I'm focusing on here. You have the mentee in the middle. You have multiple mentors that they can go to. And then you have what are called these mentor nodes. A mentor node is a rotating position. So it's not ever one person. These are short-term mentoring positions. So think of it as you're working on a project and one person in particular helps you with that project quite a bit. When that project ends, you part ways. And perhaps you work together again, but you're not working together all the time. So these are short-term cycling relationships where you're still getting mentored, you're still getting resources from that person, but not consistently. Think an academic advisor at an institution, for instance. Again, this is very useful, but it neglects having peers connected and the mentee is not mentoring themselves. So in light of that, I created my own version of this diagram in pink, obviously. So you can put yourself here. You are connected to two, well, you don't have to have two, I just put two here. but you are mentoring other people. So by mentoring yourself, the mentee will learn from you. You get leadership opportunities here and you strengthen your own physics identity because you're helping someone else through what you just went through. Then you have your peers. Your peers can emphasize and validate your struggles. So if you completely bomb an exam and you have your peers to go to and they say, I also bombed that exam, you feel a lot better about yourself. It decreases othering and increases your belonging in the field, and it reduces imposter phenomena, because if you can go to other people again and say, man, that homework was really difficult, or this person was being weird, right? And they can validate that for you, you feel less like you're lying to yourself and to others. Then you have your mentors. These are long-term relationships, multi-year, your PhD advisor, chair of your committee, something like that. They provide direct guidance and they are responsible for both your academic and personal growth. Personal growth looks different from relationship to relationship. That has to be an open and continuing conversation, but learning time management and responsibility is still personal growth, even if it's not, relationship help. Don't go to your mentors for relationship help. And then you have your mentor node, which, as I explained, is a rotating position. They provide specific guidance as requested, and it's short-term, think 6 months to a year, and you part on good terms. When I say part, it doesn't mean that you stop speaking entirely, but you're not having that close, constant contact all the time. So, I am the co-founder of an organization called Spectrum. We work on empowering equitable excellence, and we recently, it's 2 years ago, got funded to develop a mentorship training through the American Astronomical Society. We did. And so through our mentorship training, we teach to aim to be an advocate and not an ally. So an ally is someone that can say, I'm behind you all the way. And indeed, they're standing like miles behind you and letting you deal with it by yourself. Whereas an advocate is right there with you. They're stepping in front. They're using their privilege to help you instead of having you do it. You should practice culturally responsible, advocacy-based mentorship with your student. So this is recognizing that you come from different cultures, from different worlds, your lived experiences are different. It's okay to have uncomfortable conversations. It's okay to be wrong. It's about growing and understanding that your student or you come from multiple different places and that factors into how science is performed. And the advocacy-based mentorship is, again, you standing up for your student when necessary, you going to bat, making sure they get on projects, making sure that in closed door meetings, your student is not being talked about in a way that is unappealing. And especially you have to focus on this for those from historically minoritized groups, because they are the ones that end up suffering the most in this field, so they need the most help. So you should set examples of communication. You should have open conversations about teaching and learning styles, what your expectations are, so that nobody is reading minds. If you want to have weekly meetings, then tell your student you want to have weekly meetings. Or if you have a goal set for them, tell them what that is. Just keeping the communication open is a great way to minimize any miscommunications and building up feelings of resentment. Remember that as a mentor, you have the power in that situation. So even if you think of yourself as approachable, you are still a power figure, and a student may not feel comfortable coming to you and saying, I don't like the way that you did this, because they could feel fear for their position. So you have to be the one really leading that charge. You should be comfortable with being uncomfortable and uncomfortable with being comfortable. Comfortable here meaning, complacency. You should not become complacent. You should constantly be learning, growing, having hard conversations. The world is constantly evolving around us and there's lots of things happening. Just because the thing in the news didn't affect you doesn't mean it didn't affect your students in a certain way. So being open to having those conversations is crucial. Or if you don't want to have those conversations, again, say that, set your boundaries. And then we actually established separate trainings for ECRs and SCRs to avoid power dynamic struggles. Here, ECRs being early career and SCRs being senior career researchers. And we outline the responsibilities of a mentor and emphasize that one cannot be a mentor in a vacuum. Just because you call yourself a mentor does not mean you are one. You are only a mentor if a student or early career researcher of some kind views you as a mentor. The only way that changes is if you sign up for a mentorship program and you are a mentor then. But just because you call yourself one does not make you a good person. Just because you call yourself one doesn't make you a mentor. Sorry. So conclusions for mentorship. There are many barriers that harm the recruitment and retention of historically minoritized groups in physics and astronomy. The upcoming Habitable Worlds Observatory presents an opportunity to introduce effective and ethical mentorship practices on the ground floor of development using the START tag. And constellation mentorship combined with culturally responsive advocacy-based mentorship can be the most effective for aiding historically minoritized groups in physics and astronomy. And as I said, in future works, I'm going to be working on expanding the study into other ethnicities and races. Again, looking at Arabs and Arab Americans and their experience, although that's a whole other issue to unpack because on the census, you can't even check Arab or Middle Eastern yet. That's a whole other thing. I'll get on my shoebox. So thank you very much, everyone, for listening. This Barbie is available for questions. I know, on any of the topics, and thank you so much.
Awesome talk, Natasha. So yeah, we have time for questions. So anyone in the room, feel free to raise your hands, or anyone online, feel free to raise your hands. Yes.
Sorry, I was want to make sure I was visible from
Yeah,
my
yeah.
line. Thank you for the talk. That was really interesting, and I really enjoyed just like how deep you went on the mentorship stuff. I've got two questions, if I can sneak them both in. The first one was you discussed doing separate mentorship trainings for early career and senior career researchers, and I was wondering if you could talk more about what you were doing differently in them and what type of dynamics you were trying to create by separating those out. And then the follow-up one, let's just do one. We can throw back. I'll wait.
Sure.
Yeah.
So by separating the early career and senior career researchers, even though the same material was generally being covered in both, we had a role-playing component to our mentorship training. And so the role-playing case studies were different. So the ones for the faculty or senior career researchers were the ones where they were the ones in power in that situation, versus the students, they are the student in that situation. So learning how they can act safely and effectively in both of their respective positions. Especially because for students, even though you may want to speak up in defense of another student, sometimes it may not be safe for you to do so, whereas for a senior career researcher, it's 99% of the time safe for you to do so. So teaching that difference. We also taught in the early career researchers training what to look for in a mentor and how to get yourself out of toxic advising situations. Because a lot of students fall victim to this idea that because they are working with somebody, they can't leave. I already started working on this project, they'll hate me, you know, whatever. And so teaching them how they can effectively and safely remove themselves from a situation, how much power they actually do hold in a situation, and trying to emphasize that, like, working for 6 months on one project may feel like forever when you're an undergrad, but in grand scope of things, it ties you for life to that project. It's not worth it, right? So those were the main differences between the two trainings.
Oh, yeah.
I have one question about, actually two questions, but one is fast, about the Barbie work.
Yeah.
So you showed all of these plots about the boundary between, you know, how do you say, like, strong detection and the level below, how do you call it?
Yeah, unconstrained.
Yeah, those, everything like that, you know? I was wondering, like, you have a low hanging fruit here that I see, but maybe you already tackled this. How about the threshold between unconstrained and basically like upper limit or weakly constrained, you know?
Yeah.
So that you can not only detect when, you know, you get, words are hard this point. You cannot, you know, basically knowing the edge between unconstrained and weakly constrained would also help you out when identifying a promising target in a
Yes.
way, you know, so have you worked on this part? You know, maybe also already using this data that you already have.
So we used it, we looked at it using this data very briefly. We
Okay.
wanted to focus on strong detections, mostly because the strong detections ended up being a lot more accessible than we thought they were. But we focused more on the weak detections when we were looking at O3, for instance, because strong detection basically meant nothing
Right.
at here because of the high SNR required and the abundance is required. So we looked at weak O3 detection.
But you could look at all the other ones so that you know, like when you observe the planet the first time, you don't necessarily have to go to SNR of 10. Maybe you're good
Right.
with like SNR of 3, and then you're like, okay, good, let's keep looking at this. So like
Yes.
as a first funnel.
Yeah, so we have the, dang it, I put them on a skip slide. But we do have those for H2O and O2. The O2 weak detections are actually the same as a strong detection.
Okay.
It's just for like the very, like it's just here.
Mhm.
For the SNR.
Okay.
It's just the same though. Yeah, but we did look briefly at that. The idea would be that we would explore it more firmly in Barbie 4, spoiler, there's a Barbie 4. When we look at the different molecules through wavelength, through SNR, through bandpass, and that's when we're gonna do basically what Barbie 1 and 2 did, but over the entire new swath of new, molecules. Barbie 3 is really just introducing Ken and validating
Oh, and by the
Ken.
way, what does CAN stand for? It's an acronym, right?
It is an acronym, thank you so much for asking, but it actually doesn't stand for anything,
Okay.
it's just Ken.
Sorry, that's that.
Thank you.
That was the second question.
You just asked the best question ever.
I had a question sort of related to this, so the your detection metrics. I was wondering, you also get from your grid-based retrieval also posterior estimates, right? Around your abundances, but you translate this then into this detection metric, say strong weak detection. But could you refer this then back to an uncertainty around a specific species abundance in the atmosphere? So could you then, is this basically correlated, right? Your strong detection is correlated to a narrow and less biased posterior, for example, around that abundance.
Yes, so we do take a look at the posteriors very briefly in, yes, Barbie 1, did you do it in Barbie 2? Do you remember? I don't remember. Okay, corner block.
Definitely do.
Definitely 2?
Right.
All right, so we look at it in both Barbie 1 and Barbie 2, because we actually see, careful. So the first thing that prompted us to look at it is here in H2O, you can see that even though we're strongly detecting H2O, we're actually, we're retrieving an abundance over the true value. And it always happened at 0.9, no matter what we did. And so when we took a look at this is why we present the posteriors in our paper, because we were able to find that actually H2O and pressure are very strongly correlated out in these wavelengths. Which is why at these wavelengths, you're getting a strong detection, but an abundance over your real abundance. Whereas at lower wavelengths, you're actually able to get closer to the true value for water, for O2, for O3, because the continuum allows you to get a better handle on the pressure estimate as well. So very long way of saying, yes, we do take a look at the posteriors as well. The corner plots are also pink and they're in the paper.
Great, let's go.
Oh, do you have it open?
No.
Okay.
Probably a kind of quick question. I know that the HWO team has a DEI group, and I believe Evan Scanapieko is one of the leads for that. How much overlap is there between the mentoring conversations and whatever the DEI group is doing? And I wonder, have they invited you to talk? Because it seems like they kind of should.
So the DEI and mentorship groups are actually the same. They've combined them for now. I think they have this vague idea that they might separate them out later, but they actually haven't started doing very much yet. Joe, you're on the committee.
So I am the co-chair for mentorship for HWO. And yes, we are slowly spinning up things, and we would love to talk to Natasha more as soon as we get our stuff together. But yes, so yes, as Natasha said, there is a DEI and mentorship working group. And then there are 2 subgroups. So I'm a co-chair of the mentorship and then other folks, but Evan is chair of the, Evan and Rachel. Oh no, I forgot the last name. Beaton, yes, are the chairs of the DEI, like the super group of that.
I did not mean that question to shame you.
Oh, no, it's okay, it's okay.
Shame it.
Yes, please shame, please shame. Yeah, it's.
Are there any?
Yeah, Toby.
I have like 2 questions. One's really quick. I'm not really sure, I'm not a big expert in this at all. What is beta?
What is
What is beta? That you're-
beta? Oh, so it's natural log of beta is the, it's just the log Bayes factor. So the Bayes factor is calculated by taking a spectrum that has the molecule that you're interested in it, and then it has the molecule removed from it. And you subtract these 2 and figure out which one has the best fit spectrum, and that's beta. And then you look at the log of beta, and then it scales. I mean, it can be any number, but from 0 to 2.5 is in our simulation unconstrained. 2.5 to 5 is like a weak detection, and then and then 5 above 5 is a strong detection. So that's what beta is, and it's defined for the first time by Beneke and Seeger in 2013, somebody correct me if I'm wrong.
Actually, Jeffries defined it first, but then Bennett and Seeger created this correlation between the Bayesian way of saying it and the frequencies way of saying.
Okay,
Right, so that they have the connection to the sigma.
yes, they do.
It's actually, just to make it clear, like it's the ratio between the evidences, so the Zs, but then if you do the log, it becomes a difference. That's why she said difference, subtract, because it's a log scale.
Yes.
That's all. Yeah, it's okay, it's fine.
Thank you, Elena. She's got my back today. Of course.
So, I don't know how far along you are in your project, but have you implemented, this in like George Mason as well, in university?
For the mentorship? I've tried to.
It's funny how all the
There.
people doing mentorship come from your place.
It's kind of the whole despite George Mason of doing mentorship kind of thing.
Are you,
Wow.
like, are you looking to like implement or like give this idea to like anyone at other universities to see if they can?
Oh, yeah, I'm glad you asked. So, Spectrum actually has a starter kit for creating sister institutions, and it includes the entire mentorship training in it. It's all free. All including my time. And then I think, was there a question online?
I think Yesenia had just a comment for you, but I think we have time for one quick question. If you have a quick question. Yeah, go for it.
Yes, great talk. That alone was worth the flight from Switzerland. 2 hours in immigration yesterday.
Oh,
I have a bunch of questions. Probably when I got over my jet lag, I'm gonna ask the rest. So just quickly, so what is a typical observation time to get a signal to noise of 12 at resolution of 140 for the first twin?
That is a phenomenal question, and I don't know the answer, Vincent. I'm
It's-
We have to look at a little more, depends on like what wavelength range, what object, what distance, but we've definitely done a whole bunch of simulations together, so if you wanna see the Excel sheets or see the.
I mean,
how
just
we do it,
ballpark, is it 10 days or 100 days or 1,000 days?
For signal to noise of 12.
First twin and 5 or 10 parsec.
I was, yeah, that sounds quite reasonable.
It's about 10 days. What we did for our simulations, because for PSG, we can set a signal to noise ratio and it just say, this is what I'm getting for the spectrum. So we skipped all of the part of actually calculating it and just said, assume I got it. So, but for an SNR of about 12, I think
Just
it'd
an
be about 10
engineering
days. It's an engineering problem, they can figure it out. So yeah, but for an SNR of 12, it's hand wavy about 10 days. Which is why we call it an accessible, because for a, for a target of reasonable importance.
Well, what we did for another study was essentially look at how long you need to observe to get to a signal to noise ratio of 5 for a certain spectral feature. And I have a bunch of, sorry.
Isn't it, Rhonda presented it also, Rhonda Morgan from JPL with like the depths, like the water
Yeah,
feature and.
she's looking at like just finding exoplanes. She doesn't, I don't think she characterizes spectral signatures, but she's you guys are wrapped up. We can talk about it.
Yeah, I think we have to give up the room, but let's thank Natasha again for a great talk. Thank you everyone online for joining. I'm gonna end the meeting now.
Thanks, everyone.